Welcome to week 3. I'm sorry, I teach multiple schools and I'm losing track of which week is which. Lab 2, the measurement of density. So we're going to be talking about where extensive properties, and those are properties that depend on the amount of something like mass or volume, meets intensive properties which are independent of amount, like density. So that's what we're going to be talking about today, and the best way to start any story about science is with a story. So we're going to go all the way back to 265 before Common Era, and King Hero was just named king of Syracuse after a series of victories in a war, and he decided that he needed a crown. So he took an amount of his gold and he took it to some priests to bless so that it was holy gold, and took it to the goldsmith to make him this laurel wreath crown as shown here. And it's not the exact one, of course, but a replica. And was all set. The crown was made and was going to be anointed in a big ceremony. And the word was around the kingdom that the goldsmith was a little heavy. He got a little extra pocket money. And the rumor was he had stolen from the king. And so the king, of course, infurious, as all kings would be, because they're pure pride, he calls in his scientist Archimedes and he says, "Archimedes, I need you to tell me whether I was cheated. But there's a rule: you can't touch or destroy the crown in any way, because if I wasn't cheated, well, then it's a holy crown blessed by the gods, and even you can't destroy that." And so Archimedes thought about it, and he couldn't figure it out. So he did what some of us do when we can't figure out a problem. He went home and he took a bath. And it didn't take him long. As he was getting into the hot bath, he filled it a little bit too big, and as his volume entered the bath, he displaced water, and it splashed over the sides, and he stood up and he had his eureka moment. And so he immediately jumped up and he ran to the king. No, he got dressed, and then he ran to the king and says, I figured it out. So let me stop and say there's a few things they knew at the time. Two things. The first thing was that of this idea of density, that if you take one pure substance, that every mass you have will relate to the volume of that mass by a certain constant number called density. So density is the relationship between mass divided by volume, and it's always constant for pure substances. The other thing that they knew was that you could alloy materials, and that is taking two metals and melt them and mix them to have kind of a combination of properties. And you could alloy silver with gold in small amounts, and it would still look like gold. But he knew that the density would be some sort of weighted average of those two densities, which means that the density of an alloy of gold and silver, because gold is 19.32 grams per mil and silver is 10.49, much less grams per mil, that the weighted average will have to be in between there, i.e. it has to be less than gold. So he took a new collection of gold from the king of the exact same mass that the crown should be. And he put it into a bucket of water and he filled the water all the way to the top. And then he very carefully reached his hands in and removed the gold. You can see there maybe is a little bit of room for error here, but we'll forgive him. And he put the gold aside and the water sank down. Now, if the same mass of gold was used in both objects and the density is the same, their volumes would also need to be the same. That means that when you put the crown in, the water should fill right back up to where it was. If the density is less because it was alloyed with silver, then the same mass would require a larger volume, and you would expect the water to splash over the sides as it did in his tub. And so what history tells us is that when he put the crown into the bucket, water spilled over the sides, indicating that the king was in fact cheated, and the goldsmith promptly lost his head, which is sad. So this idea of density continues today, and we're going to do an Archimedes style experiment, but with no death, looking at density. So density, again, is this relationship, this ratio of mass per volume, and it's constant for a substance. The SI units are grams per centimeter cubed, as volume. The SI unit for volume is meter cubed, not liter. Fun fact. Or grams per mil, as we commonly reference, because 1 centimeter cubed is 1 milliliter. And this connection is going to be really useful to you going forward. So just a few examples of densities of materials. We have chlorine gas at STP. The density is both pressure and temperature dependent in a gas, is 0.003214 grams per mil. So not very dense at all. And we know that about gases. We walk right through them. Water, on the other hand, at 4 degrees Celsius, famously, is 1.000 grams per mil, 1 gram per mil water. And we normally just make that assumption, 1 gram per mil, at pretty much any temperature. But just note that it only at 4 degrees C is at exactly 1 gram per mil. And then solids like sodium chloride have a much higher density, and we know that. Rocks sink in water. The density of sodium chloride is 2.160 grams per mil. So we are going to be measuring both mass and volume tonight. So we have to start by talking a little bit about what it takes to measure volume. And there's a few things we should know about. The first is the meniscus. The meniscus is this shape that water makes, or most liquids make, in a glass container. And it's a little smiley face curve. And the reason I want to talk about that is because somebody who has never taken a science class before and sees this could think one of two things. They could think that at the edges here, the water is rising up, or at the center here, the water is sinking down. And depending on what you believe, you might take a measurement in a different place, and thus we could have some error in the way we take our measurements. So here's the answer. The answer is that the polarity of water, if you don't understand that, you will by the end of this course, but think of it like the stickiness matches well with the polarity of the glass, or the stickiness. And the water actually climbs the side a little bit. And I tell you that because then it answers your question, and you can see the meniscus and say, in the center, it's not dropping down, it's just not climbing the glass. And at the edges, it's climbing the glass. So the consequence is that when we read a volume in, say, a graduated cylinder, as we're gonna do tonight, we're gonna look at the bottom of the meniscus, right in the center. Another thing is that there's this idea of uncertainty. So in an analog instrument, in a glassware instrument, where we're reading tick marks, where we're actually the brain that is collecting the data, we want to estimate that last digit. We want to give ourselves as much significance, and we'll talk about that in just a minute, to our measurement as possible, because our measurement is what dictates how many significant figures we can report at the end. So getting as many decimal points, as many significant figures in our measurements is absolutely critical. So our glassware is going to let us know what the uncertainty of the glassware is. So for a graduated cylinder tonight, our uncertainty is 0.5 mils. And what that means is if you look at the instrument, you can see that there's marked every 5 mil increments. And then the sub-markings, the minor markings, are every 1 mil. So you can very easily see 20, 21, 22. So what it asks for you to do is to estimate one additional digit. But it's weird, it says 0.5 mils. What does that mean, plus or minus? The idea is that these hash marks are too close together to separate with an eyeball into tens. You couldn't really tell the difference between 22.4 and 22.3 by eye. So what it says is that you can guess one of two things for that last decimal digit at 1/10 of a mil. If the meniscus is exactly on the line, then you will report the last digit as 0.0. So 20.0 mils would be a reasonable measurement for this graduated cylinder. If it's anywhere between the lines, we're just going to call it 0.5 mils with whatever the rest of the measurement is. So whenever you're measuring with a 100 mil graduated cylinder, you only have two options for that decimal point. It should either say 0.0 or 0.5, and it should always be there.
I have a quick question.
Sure, go ahead.
What if you were measuring out of a 10 millimeter tube? How would you
a 10 mil graduated cylinder?
How would you calculate the value for that?
Are you saying that it's a different instrument or a different volume, or is it exactly 10 mils? I'm sorry, I'm just trying to clarify.
Yeah, exactly 10 milliliters.
Okay, if it let's say 20. If it landed right, if the meniscus, if this red dotted line was right on the 20, is that what you're saying?
Yeah, but I was just...
Fantastic question. Great question. So then you would say 20.0 because it's on the line. You add that 0.0. And we're going to see in a second why it's important to add that extra digit. We're allowed to add that extra digit according to the glassware's uncertainty rules. And we want to, because if we just put 20, we'd only have 2 sig figs, and that is going to limit what we do at the end, how accurate we are at the end. So it would be 20.0. So if it's exactly on the line, then you put a 0.0, and that is your estimated digit. Does that answer your question?
No. What about the, because I'm more concerned with the 10 millimeter graduate cylinder. Like, would you measure it with two significant figures after the decimal point, or would it be one?
So with the 10 mil, I'm trying to recall, and I should have grabbed it from my daughter's room, but I'm pretty sure that the uncertainty on a 10 mil is 0.1 mil. But you would look at the glassware, it actually says right on the glassware on what is the uncertain digit, what's the guessing digit, and then whether or not you can guess plus or minus 0.1 if it's discernible in tenths, or whether or not you have to guess plus or minus 0.5. Some glassware says plus or minus 0.2, so you can only guess 0.2, 0.4, 0.6, 0.8, or 0. So it'll show you on the glassware, and then because we're doing these digital simulations, it's really important that, you know, in this pre-lab, I tell you about what the uncertainty for the glassware will be using, and if you're ever unclear about something you're using in the simulation, just ask your instructor, and they'll be, you know, they'll be able to tell you about any piece of glassware's uncertainty.
Okay, thank you.
Cool, thanks. So if we zoom in now on our measurement, we can see that it's between the two lines, which means that we're going to have a 0.5 of hanging digit. And so we say that this is 22.5 mils of measured volume. So today we're going to be finding the volume using the Archimedes method, right? So he was measuring gold by the volume of the gold by having a lower volume of water, and then he put the crown in and the water raised up. So there was an initial volume, and he added the volume of the solid, and then there was a final volume of the tube. So we'll be calculating that by the volume of the solid equals the volume final minus volume initial, and we'll get to that in just a bit. One more thing about uncertainty, the other thing we're going to be measuring today is mass. And so when we're measuring mass on a digital scale, so anything that just gives us the readout, there's no guessing. We just report the significant figures and the numbers that it gives us. And that might be a balance as tonight, but going forward, we might use a digital thermometer. There's also analog thermometers, and they'll have their own uncertainty that you'll need to apply. But then for digital thermometers, you would just read what the display says. And this is a digital caliper, which of course would relate to the analog ruler, which again would have an uncertainty that you would read on the ruler, and then you would estimate that last digit in the way it tells you to. Or you could use a digital caliper that is more accurate, and it's not going to be, you're not going to have any estimation. So estimate if it's analog, report it directly if it's digital. And keep in mind that our final calculation is only as accurate as our least accurate measurement. So whenever you're trying to do really accurate work in a lab, you want to make sure you appreciate that all of your measurements need to have as much significance as they can, so that your final calculated result has as much significance as you can. And we're going to talk about how to calculate sig figs right now. So in your pre-lab information, and if you say, I don't know where the pre-lab information is, I'm going to show you in just a minute if you haven't read it yet, and you can read it there. But in that, they talk about how to calculate sig figs. Also, your textbook and plenty of places online are going to tell you how to calculate sig figs. And all are going to have maybe a slightly different take on the order of the rules. So what I recommend is listen to this version, read that version, and just understand we're all saying the same thing, but this is a really important thing to get down and be able to figure out how many sig figs are in your numbers so that you can calculate with the right number of sig figs. The two biggest things that I mark down on whenever I teach any general chemistry class during the labs are units and sig figs. People forgetting to put the units and people forgetting to correctly report the right number of sig figs. So the three rules, I like keeping it simple. So the three rules are: one, make sure that the number that you are looking at has a decimal point. Then you start at the very left and you move right until you reach your first non-zero digit. You count that digit and every digit to its right as significant, including zeros in between non-zeros. So let's take a look. We have a decimal point, check. We move all the way to the left and start at the first non-zero digit, check. 1, 2, this is a 0 in between two non-zero digits. We count it as significant. 1, 2, 3. 3 significant figures here. You can do it again here. Decimal point, check. We start at the left. We move to the right, finding a non-zero digit. Check. 1, 2, 3. this number also has 3 significant figures, even though this is much less than 1, this is greater than 1. So now this number, first one, make sure it has a decimal point. It doesn't have a decimal point, so our whole system has broken down already. So what we can say about this number is we don't know how many significant figures it is because that decimal point tells us a lot. So we could say possibly, at most, we can say this has 1 significant figure because we don't know about these zeros. But I think probably a more accurate way to report it would say that this number is ambiguous. We can't really tell its significance, and we don't know how accurately, because remember, significant figures come from our measurement, how accurate our instruments that we're using to measure are. And so we just don't know from the way this number is reported. And then finally, decimal point check. And so we start at the left, non-zero digit, 1, 2, 3, 4. And this has 4 significant figures. That decimal point there is so important for us to know. So that is sig figs. When we know the number of sig figs possibly that our answer has to be, but then we get a number when we do the math on our calculator that has all these decimal points. So I'm sure that this is probably a little bit remedial for some of you, but I just want to remind everybody on the importance of how to round correctly. But remember that when you're rounding, you find the last digit that you want to report. The next digit, if it's 5 or more, you round up. If that digit is 4 or less, then the previous digit will stay the same. And that I want to remind everybody that when you're doing math tonight, that just keep the numbers as big as possible until your last step and then round to the right number of significant figures. And that'll help reduce calculator error, especially when you're dealing with small sig figs. Sometimes every time you do that rounding in the intermediate steps, it can really stray your final answer pretty far away from where it should be. So that's just a pro tip. So let's say we want to round these numbers to 4 sig figs. So we have a decimal point check, and we go 1, 2, 3, 4. So we want to round here, sorry. So this 7 then is higher than 5, so we would round this digit up. So 56.38. Again, 1, 2, 3, 4, cut it. 5 is 5, so we're gonna round up this digit. So our answer with 4 sig figs would be 105.6. And one more, not to overly belabor the point, but we start at the left, decimal point check, move all the way to our first sig fig, 1, 2, 3, 4. So we'll cut here. This is now less than 5. We don't round down now, we just keep it the same. So our answer would be 0.004564. One last thing about sig figs. Now we know how to calculate sig figs, and now we know how to round so that we get the right number of sig figs. What happens when we do math? What happens to sig figs when we're just doing a mathematical calculation and the number changes its form? So there's 2 rules that you have to master. The first one is the multiplication and division rule, which says that the final answer must contain as many sig figs as the value with the least number of sig figs. We're only as good as our least accurate measurement. So for this instance, we have 1, 2, 3. This is a multiplication equation times 1, 2. 20.2 times 4.1. So our final answer has to have 2 significant figures. So when you do this math just on the calculator, I get something like 82.82. This needs to have 2 sig figs, 1, 2. So we're going to round here. That number is 8, which is more than 5. So this answer with correct sig figs is 83. Just one more. So this is division, 122. There's a decimal point, so there's 3 sig figs. Another decimal point, 2 sig figs. So our answer has to have 2 sig figs. The least number of sig figs is our what we're allowed to report. So you divide this, and my calculator says 7.176. So 2 sig figs, 1, 2. Here's where we round 7. So this will round up. So with 2 sig figs, this should be 7.2. Of course, if there was units attached to these mathematical calculations, then I would of course want to report the proper units. The second rule that we need to know, of course, is addition and subtraction. What happens to sig figs when we add or subtract them? And now it's a little bit different. Now we're tracking the number of decimal points. So just to make sure that everyone's a little bit confused. Our answer has to have as many decimal points as the number that we are adding or subtracting. with the least number of decimal points. So for instance, here we have 3 sig figs, 2 decimal points. And here we have 2 sig figs, but 5 decimal points. So the least number of decimal points is 2. So when we add these, our calculator says, let me see, 1.27032. So we need 2 decimal points, so 1, 2. So we cut off here, it's a 0, so it stays the same. So with the proper number of sig figs, it would be 1.27. I specifically use this example because when math like this happens to students, they go, that's not right. You can't add something and get the same number back. That's not how math works. But remember, this is a specific kind of science math. And what this actually is saying is that this addition is non-significant based on this significant figure. So again, if we had measured this 1.27 with more significance, then the addition here might end up becoming significant in our final results. So we're deciding what our least accurate measurement is, and that's going to dictate our results. Okay, one more example. The 3 decimal points here, we're subtracting, and then there's 5 decimal points here. So when we subtract those, I get 1.4784. So 3 decimal points, and so it should be 1.478. And I will put the pen away now. All right. And I said no more about sig figs, but I have one more thing to say about sig figs. Go away, pen. One more note. We have these things exact numbers, and this can be a little bit confusing because you can say maybe you need to multiply by 60 seconds in a minute as a conversion factor, or 12 inches are in a foot. And so what is the sig figs? 1 for 1 minute, 2 for 60 seconds, and there's no decimal point there, so I don't even know, it's ambiguous. So exact numbers, these definition numbers, we don't count sig figs. We just consider them infinite, so they just don't count in our final calculation of what the answer sig figs should be. So whenever you're using an exact number, you don't need to worry about sig figs, and if you're confused on which is an exact and which is not, you can always ask, but just remember that you should be getting the numbers with sig figs come from measurements. So you should be collecting those and understanding the uncertainty from what you're using to measure. If you're using it as a definition, it's most likely an exact number, but always feel free to check with your instructor. All right, let's get into the software. So if you start from Canvas, there is a link to the Hayden McNeil lab simulation software right there on the Canvas page, so you can click where my mouse is. And it will bring you to the Hayden McNeil software page. So hopefully you have a username and password at this point, and you can enter them. Don't enter mine because it won't work. And you should get here. It's going to say, hi, Michael, you're here. And it's got this kind of ambiguous page. So if you're lost at this point, you go to My Courses. And I have a few courses, but yours should say TRO on it. It says anything else, and you're in this class, please talk to your instructor. And so then we scroll down to experiment 2 about density, lab techniques and density, and that's what we're doing today. And I just wanted to point out that this green book that says 2 lab techniques and density, that's where the background reading and procedure reading is. The pre-lab and post-lab are below it, and we will, I'll talk about those in just a second, or not in a second, maybe in a few minutes at the end of the lecture. But we'll click here first, and we will arrive here. Now I'm gonna kind of just pass this point, but I don't want you to think that it's non-important. This is what you should absolutely be reading before you're doing the pre-lab quiz. So they're gonna be talking about density, they're gonna be talking about significant figures, they're gonna be talking about uncertainty. And so you're gonna get a good sense of the questions asked in the pre-lab. You're also gonna be better prepared for this lecture and for jumping right into the lab. So make sure you read the whole thing. At the bottom, there is an arrow to progress, or you can come back up and go to where my arrow is, where it says procedure. So there's 2 options, background and procedure. When you go to procedure, it should look like this. So this is where we're gonna be doing our experiment today. And if you scroll down, this blue box that I'm clicking on, that's where the actual lab is hiding. And so what I want you to do, because the rest of this page contains the instructions, step by step, what you have to do. So if anyone is freaking out, and as I talk through the lab and say, I can't keep up with this, you're gonna have all the step-by-step instructions that I had when I did the lab. So don't worry too much about it, but know that you're gonna need them. They'll be really helpful. So opening the lab, the digital lab, in either a new window or a new tab allows you to then have either side by side or up and down, however you wanna arrange your screen, your experiments, and then the instructions below. So I recommend using one of those 2 things. So I opened it in a new window. It looks like this. You enter lab. So the first thing it's going to ask you to do is make sure that you're wearing your PPE, your personal protective equipment, goggles, lab coat, and gloves. Now, I am well aware of maybe the exhausting nature of online learning and that adult learners don't want to be placated. They don't want to be treated like children. But this is what I'll tell you. When I was doing undergrad research, I remember this one day I did research in a lab that dealt with really strong acid chemistry. So stuff that was really corrosive, and if you spilled it on yourself was a really serious lab accident. And I was working in the lab on my own thing, and somebody had started an experiment and walked away from it. And all of a sudden I heard a loud noise and felt cold water on the back of my neck, and I froze. I was so concerned, and it turned out that it was a water hose for a cooling line that burst, and it was simply water. But in that moment, I had realized, of course, I was wearing goggles and PPE, but the liquid got onto my neck, that two things. One, that wearing PPE is critical at all times in a lab. And two, that your safety is not just based on what you do, but what everyone is doing in the lab. And someday, we're not going to be doing digital labs. You're going to get a job, or you're going to go on to additional classes where you're going to be in face-to-face labs. So just thinking PPE every time you walk into any lab is extremely wise. From scientist to scientist. So I just want to point that out, that this might seem silly, but just take a second to say, if this was when this is face-to-face, when this is real life, I'm going to need to make sure I have goggles, lab coat, and gloves on before I enter any lab for any reason. And then you can enter the lab. All right. So this first part, I'm going to kind of go through a little bit more clearly, because sometimes the simpler tasks seem confusing because people look for them to be more than they are. So it's going to ask you to take out 3 pieces of glassware, the 250 ml beaker. So what I'm going to do here is show you where you click and then where you drag. So you can drag it anywhere on the lab bench. This is your space, but you just click on the 250 ml beaker, the 50 ml beaker and drag it, and then the 100 ml graduated cylinder, and they look like this. And then what it's going to ask you in the instructions is to put anything between 30 and 40 mils of water into the glass. So here's the water. So you just simply grab the water off the material shelf, drag it over to the 250 ml beaker, and then release. And it will bring up this prompt and says, how much do you want to add? And the instructions, then the procedures say anywhere between 30 and 40. So I was feeling dangerous this weekend, so I said 33. But you can put in whatever you want. And it looks like this. So you can kind of hardly see the liquid is down there. There's a zoom button down here, and especially if you've highlighted the beaker or the whatever the instrument is that you want to look at, it will zoom directly in on that object like this. And this is where the first part I think students are going to get confused, because then the task is record the volume here and say, I can't really tell. That's the point. Truthfully, as much as I don't want to take away the punchline of this portion of the lab, that's the point. When you look at a beaker in real life, it actually says approximate values right here next to the numbers. You're never meant or intended to measure out exact volumes of liquid with a beaker. They're meant for doing reactions and holding liquids in them. And so do your best to measure it, but just know that if I can't really tell, it's between 50 and 25, something like that, maybe closer to 25, 30. I mean, we know how much it is, but you can't really tell. That's the point of this. So just do your best there. And then what it's going to ask you is to transfer the water from the 250 ml beaker to the smaller beakers. All you have to do is click on it, drag it over, and it will look like this. It's a little pouring mechanism. And a prompt will come up that says, you can either dispense a certain amount of that liquid. I don't know how you would really do this in real life. But up to 33 mils, because that's what me living dangerously added. Or you can pour all. I want you to just pour all. Just transfer it. Zoom in on your smaller beaker with your 33 or 30 to 40 mils of water, and just record what you think it says. And then when you're done, digitally transfer it to the last instrument, which is the graduated cylinder. So just do both of those. So this is the transferring it again to the graduated cylinder. So here it is. So I've looked at it in 3 instruments. I'm going to zoom in, and now you can see much more clearly that it looks like it's exactly on the 33 tick mark, so 33.0 mils in the graduated cylinder is what I would read there. And the point of this is just before we start measuring volumes is to recognize that while we're doing it like Archimedes, we have better instruments than Archimedes. We don't need to use a wooden bucket. And so we need to know what is the glassware instrument that helps us measure volume, and it's not beaker. And what all of us lab instructors want is that someday you don't go into a lab and try to measure out an exact volume with a beaker, because your boss will be like, what the heck? So use a graduated cylinder, and this is really just to prove to you that it is the obvious superior instrument for measuring volume. When you're finished, you need to pour the water into the waste container. And so you just drag it over the waste container and it will look like this until it drains in. Of course, we're using water today. And again, even if we were in the real lab, you could just pour that down the drain. But again, because we're trying to learn labs in this digital space, it's important for us to take a step back for some of the really important things, such as waste disposal, and recognizing that when we do work on a lab bench, most of the time we're going to be generating waste that can't go down the drain. And there can be some really serious consequences for that. I remember that in the undergrad institution that I went to, the chemistry building had 4 floors. And so first years did labs on the first floor, second on the second, and so on. So you kind of moved up the building over the years. And the first years would be the ones who would accidentally pour the wrong waste down the drain and not in the waste container. It's an old building, and so these solvents would evaporate in the drains and then come up upstairs. And when you reached all the way to the 4th floor, if people were pouring stuff down the drain, it would be coming out of the sinks upstairs and making everybody dizzy. So there are real consequences. And of course, beyond that, health issues, having toxic waste into the water supply. So considering waste and waste disposal is important. So you won't be able to progress any step of the lab. It won't let you just throw things in the sink. So just know that that's going to be a requirement every time you transfer from one section to the other. Okay, and then you can put everything in the sink until the end of the digital lab. So now I'm going to quickly talk about parts experiments 2 and 3, which are really kind of one thing. So now you're going to be needing a balance because we're getting into density, right? So we have volume and mass needed for density. And the first part is measuring the density of liquids. So we're going to take a balance. And of course, our 100 mil graduated cylinder, actually that's like a 50 mil graduated cylinder, but the graduated cylinder, and we are going to put it on the balance and get an initial mass. So this is the mass of the empty graduated cylinder without its liquid. We're first going to start by calculating the density of water. So you just grab the water from the shelf and add it by dragging it over the graduated cylinder, how much you want to add. So the instructions say 10 mils. So add 10 mils of water and push add. You're going to get a new mass on the balance, which is 85. So now you can do final minus initial on the balance to figure out that you've added 10.000 grams of water. You also know, because of the graduated cylinder, and again, this just comes from the fact that you told the machine to put 10 mils in, and that we can record on our graduated cylinder this one extra digit, that we have 3 sig figs, 10.0 mils of water. So then we can calculate a density, which is 10.000 grams divided by 10.0 mils, which is a density of 1.00 grams per mil, which we talked about in the beginning is what we expect for water. Not that exciting, but bear with me. So now we're going to do this twice more, and I'm going to show you at the end. We're going to make a little graph, and the graph is going to give us our density. It's not going to be hard. You can use Excel or you can use Logger Pro, and I'll show you what those graphs look like. But we're going to then add 10 more mils, so then 20 mils total, and record the mass there. And then we're going to add 10 more mils until we've added 30 mils. So 3 runs of each liquid, and calculate and recording the mass every time. Please, please, for everybody's sake, record your data carefully and neatly. I'm going to show you at the end where you're going to need it for the post-lab questions. But one of the worst things you could do is to work all of the way through this lab and get to the post-lab and be like, well, I didn't write anything down. And then you'll be stuck. So make sure that you're taking your recording of data really seriously through this process.
You're going to drive home?
Sorry, is there a question?
Tomorrow now?
Okay, so sorry, if you can mute, I'm looking for the mute all button. Thank you. Sorry, not you, it's just me, I get really distracted. So now you can do the same thing with ethanol. So just add 10 mils of ethanol while it's on the balance. and record the mass every time you add a 10 mil aliquot to the graduated cylinder. So you'll get 3 added volumes of 10 mil and 3 specific masses, and you'll be able to calculate the density that way. And then finally, the last, so that's the water and the ethanol is part experiment 2. And then experiment 3 is done with the same protocol, but now you're using an unknown liquid. And this is where it gets fun. Just like with Archimedes, the idea, the joy of science often is exploring the unknown, right? So wanting to know whether or not, you know, the goldsmith actually broke the law. So we want to discover what this unknown liquid is by measuring its density. So do the same thing, add 10 mil aliquots to our graduated cylinder, mass it every time, and record your data very carefully. And then at the end, you're going to have a table, and I'll make sure I show that to you before the end of the lecture, of known liquid densities, and you'll be able to match your unknown liquid to one of those densities and determine what your unknown liquid is. So that's kind of cool. And so now we're going to do parts 4 and 5. So again, kind of paired together, where experiment 4 is going to be determining the density of some known materials, and experiment 5 will be using that same protocol to do an unknown material. So we're going to add water, and we're going to be measuring the density of a solid this time. So slightly different. This is much more Archimedes style. So drag the water to our graduated cylinder on the balance. This time, just to make you a little bit confused, we're going to add 20 mils. So make sure that you're reading the protocol clearly, but you're going to add 20 mils. And so you see that because the density of water we've already determined is 1, so we have 95.000 grams on our balance. That's our graduated cylinder and water, but that's the initial mass because there's no metal, and we're determining this density of a solid, the iron metal density. So now it asks you to add a specific mass of the metal, and so you're going to add exactly 15.000 grams of metal. This is a really good place to say that if this was an actual experiment we were doing, I would say to record as close to 15 grams of metal as you can, but the most important thing is to measure the exact digits on the balance, not try to get exactly 15 grams, because it's not really possible to get, when you're doing the measurement, 15.000 grams. It's unlikely you would ever measure that out intentionally. And if you do, you kind of pat yourself on the back for getting it so close. But the most important thing is just to record the accurate number. But here our computer is always going to give us an exact number. So just know that normal lab procedures, we would say get as close to 15 as possible, but record the exact mass that you add. But here we're just going to add 15 grams. And then we'll see that that 15 grams is registered in our balance. So that's 110. So 110 minus 95 grams is 15 grams of iron. So we can double click on our graduated cylinder at any time. And I specifically think it's really good at this part of the experiment. And you get this meniscus reading. So this is nice because you zoom in on that meniscus. And so now we're already experts and we know how and where to measure the meniscus, which is at the bottom of the curve. And so we know that the initial volume was 20.0 moles because we told the water to add that much. And we can see that the meniscus falls exactly on that line of 22. So we can say that that's 22.0 mils. And so we subtract final minus initial, a la Archimedes, and we see that the volume of the metal that we added in is 2.0 mils. And so if you divide the mass that we added by the volume that metal takes up, you get the density. Oops, that says water. That should say iron. My apologies. Should be 7.5 grams per mil. And in fact, iron's density is, I think, 7.86 grams per mil. So where did our accuracy go in this? Well, it went the way of the sig figs because unfortunately our volume measurement only had 3 sig figs. And then the rules of sig figs means that we only carry 1 decimal point. So 3 sig figs in this mathematical operation became 2 sig figs. And we're only as accurate as our least number of sig figs. So in this mathematical operation, we can only report 2 sig figs. And so you can see that if you want to be able to report more accurate measurements, you have to, or more accurate calculations, you have to take more accurate measurements. So then again, we're going to do this multiple times. So you're going to add 3 more times amounts of 15 grams of metal until you've added 60 grams total for 4 measurements this time. And you're going to calculate or measure the volume each time so that you can calculate the density. Again, please record this data carefully and neatly so that you're able to answer the post-lab questions lickety-split and move on with your life. Then you're going to repeat this procedure with aluminum. So that's your other known metal. Adding 15 grams at a time, measuring the volume, recording your data really carefully. And then the last experiment, experiment 5, is again, it's the same procedure, but we're using an unknown metal. And we're going to try to determine, with having a list later on and calculating the density of our unknown metal from mass and volume measurements here, we can determine what our unknown metal is. So once we've collected all of that glorious data, then we can return back to this screen and do our post-lab assignment. So we click on that and it should just say start or something along those lines. I was going back and forth and it was telling me that I'd already previewed it, but just imagine that I'm clicking on a button that says go, like a quiz in Canvas. You're gonna go here. And so again, I mentioned, make sure that you record your data accurately because you're gonna need it. So here's where you'll plug your data in, the volume that you record from that beaker and the graduated cylinder. Here's where you're going to input your data for the masses and the volumes of your density of the liquid. And then it's going to say using Logger Pro, or it should say Excel, but you get the idea. So make a graph of mass versus volume, and then the slope should equal the density of the liquid. So I use hexane, so nobody try to rush and do this, and this is definitely not one of the unknown options, so I picked something else, but this would be the volume that I'd be adding, 10, 20, 30, and then I would calculate the mass recorded every time and report that, and then put a trend line and make sure that I have my equation here. R squared, or the COR, is 1, which is maximum. Why? Because this is artificial data and it's made perfectly. And so you might get an R squared of 1. You shouldn't expect that with real world data, but just keep that in mind. But the slope now is 0.672. The units of the slope are grams over mils, grams per mil. So the slope of our line, when we graph our data in the correct orientation of the X and Y, gives us our density. So the density of hexane is 0.672 grams per mil. So that's what that would look, and you're just gonna input that, upload it right here into this area. So there's a little drag and drop area for your file. And then here we go. So I mentioned for experiment 3, the part 3 with the unknown liquid, you would be given a table. So you see there's different densities here. You do your calculation of your unknown liquid. It should have a density of 1 of these. And so you say, oh, we calculated 1.26, so it's glycerol. And so then I would click glycerol. So that's where you determine your unknown liquid. You're going to input your experimental data for the masses, for the unknown metal. Same thing, you're going to create a graph, and the slope will be the density. And so you can determine the density of your metal. And then you have a list, zinc, tin, copper, silver, with different densities. And whichever density your unknown metal calculates to from that slope, then you can pick one of these. And then there's just a few extra questions. You can see 22 questions, kind of just like last week. And they're not going to really test you as long as you are familiar with what you're supposed to be doing and you follow along and you take good data. Then these questions should be pretty easy to handle. And then if you can't handle any of them, that's what the instructors are for, waiting in the lobby, ready to answer any questions that you have. So after that, I think we're just ready to do it Archimedes style, unless there's any questions. Any questions?